So now it's in a linear form. And so what you could do to estimate this Cobb-Douglas production function in your econometrics class, you could just measure output in natural logarithms. You could measure your capital input in natural logarithms. You could measure your labor input in natural logarithms. And then you would have an equation. Let me just simplify the terminology here. Let Q star be log Q. So this is Q star equals A times K star plus B times L star, where star now denotes natural logarithms. So if you measure Q, capital, and labor in natural logarithms, you could just run a linear regression. And your linear regression would give you coefficients on K star and L star. And those coefficients would be the exponents of the Cobb-Douglas production function. All right, so it's an illustration of the use of those rules. All right, we just have enough time left to talk about an optimization problem in chapter 10. And the optimization problem we're going to talk about is one of wine storage. You know, if you buy expensive French red wines, Bordeaux, a lot of times the wines will improve with age. In fact, a lot of times they'll need age to bring out the best qualities of the wine. And let's illustrate this idea. The optimal time of wine storage. Imagine you bought some wines and the value of these wines will increase with time. And you want to find the optimal time to stop aging these wines and then go ahead and sell them. But let's assume there's a precise formula that will give you the future value of wine. And the future value of wine is just given by this formula right here. K is the value of the wine right now. But then you take the constant times e to the square root of t power. So this formula right here, let's assume, gives you the future value of wine. You can see if t is 0, e to the 0 is 1, so they're just worth k right now. But you want to figure out, if you allow them to grow, if you allow them to age, the value of the wine will be worth more. So how would you decide when to stop aging the wine? What is it you want to maximize? Not the future value, because we know money received in the future is not worth as much as money received right now. So what is it that you want to maximize? Not the future value of the wine, but the what? I'm sorry, I don't hear very well.
The present value?
The present value. And you want to maximize, you want to stop aging the wine when the present value of the wine is as high as possible. Because see, as I said before, money received in the future is not worth as much as money right now. So you want to maximize the present value of the wine. In fact, given this formula here, there is no maximum for V, is there? Because V continually gets bigger. But that doesn't mean you let them age forever. Because maybe they're growing very slowly in value at less than the interest rate, so you'd be better off selling them. and their growth rate gets less than the interest rate. So let's assume that the continuously compounded interest rate, and actually let's just use a number for this. I know this number is kind of high, but I've been teaching for a long time. At one point it wasn't so ridiculously high. So you require a rate of return of 10% per year on your investment. Okay. Then what would our objective function be? Now, Ian, what is it we want to maximize?
Okay.
We want to maximize the
Present value.
present value. And how, we got the future value, so how would we get the present value?
Divide both sides by e to the square root of t.
Yes. What, no. How do we convert a future value into a present value?
By solving the equation for k. Like that would
No,
be the formula.
no, okay. So this is a little bit tricky. Let me just help you out here. We want to maximize A. And A is the future value multiplied times what? How do you convert the future value to present value? You multiply the future value by e to the minus RT. Remember that formula for present value? It's b times e to the minus RT. Now what makes this a little bit confusing, Ian, is k and a are not the same here. Because the present value is not going to be a constant, it's going to depend on what t is. Nevertheless, we know what the future value is. The future value is this, it's k times e to the square root of t. Okay, so you multiply that by e to the minus RT. This is b. Just multiply b, which is given, times e to the minus RT. And actually, we can add those exponents on e, and we can rewrite the a is equal to k times e, and e is raised to the square root of t minus RT power. And what will make this a little bit easier to do is, instead of writing the square root of t, let's write t to the 0.5 power. So if I do that, our present value, a, is equal to k times e t to the 0.5 power minus, and we're assuming r is 0.1 now. So let's just substitute in 0.1 t. So that's our objective function. See what I told you earlier? A lot of times, the most difficult part of doing one of these word problems is just to figure out what the objective function is. Okay, so that's our objective function. Now, in order to maximize A, what do we do? We've got our objective function.
Take the derivative and set it equal to zero.
Yes. Take the derivative with respect to time. See, we're trying to decide how long to age the wine. So the variable, the independent variable is t. So get the a dt, or I'll call it a prime of t. And what is a prime of t? Well, this here, Tyler, I don't know if you were the one that was gray. That is just, think of that as being f of t. So what would the derivative of a with respect to t be?
Yeah, 0.5
t to the negative 0.5 minus 0.1,
Exactly.
that quantity times, and then
Yes. So this is f of t right here. So f of t in this problem, f of t is what e is raised to, is t to the 0.5 minus 0.1 t. So f prime of t is just 0.5 t to the minus 0.5 minus 0.1. That is f prime of t. So exactly right, Tyler. So this will be f prime of t, which is this 0.5 t to the minus 0.5 minus 0.1 times k times e to the f of t, which is just this t to the 0.5 minus 0.1 t. And what do we do to this derivative? Set it equals 0. Now, this term here is always going to be positive. E raised to any power is going to be something positive. K is by assumption positive. So all that is something positive. So in order for this to be 0, what must be true?
0.5 t to the negative 0.5 minus 0.1 must equal 0.
Yes. This means in order to solve this condition, you need 0.5 times t to the minus 0.5 minus 0.1 to be equal to 0. So let's solve this equation. This will give us the critical value of t. So we get 0.5 t to the minus 0.5 equals 0.1. I don't like a t to the minus 0.5, so I'm going to multiply both sides by t to the 0.5. And then I get 0.5 equals 0.1 t to the 0.5. Now divide both sides by 0.1, and you get 0.5 over 0.1 is 5. You get 5 equals t to the 0.5. Remember, t to the 0.5 is the square root of t. Square both sides, you get t equals 25. That's the critical value of t. So what comes next? What comes next?
Plug 25 for t back into the objective function.
Okay, well,
Second order.
but that's a little premature. Eventually, we will want to do that. But we want to make sure,
Take the second derivative.
Yeah.
Max or min.
yeah, don't forget that second order condition. By the way, if you see on your test something in red that says SOC, that stands for second order condition. So if you fail to check the second order conditions, you'll see that on your test. Okay, so you would want to check the second derivative, a double prime of t. Okay, now bear with me, this is going to get, I kind of hate to do this in the last 10 minutes, but try to stay alert, because this is going to be a little messy. What is the expression for the second derivative? This will really test your differentiation skills. We've got a prime of t right here. So what is a double prime of t?
And that's
0.5 t to the negative 0.5 minus 0.1 squared.
Okay, but, let me just point out something.
Oh, right.
We've got two terms involving t. This expression right here involves t, but then there's this expression up here too. So what rule are we going to have to use? Yeah, we're going to have to use the product rule. So let's use the product rule. Think of this term as being the first term, and this term being the second. So the product rule says take the derivative of the first term with respect to t. That's the term in brackets. And what is the derivative of the first term with respect to t?
-0.25 t. negative 1.5.
Right. Exactly right. That's the derivative of the first term with respect to t. Then what do we do with that?
That times K.
Yes, multiply times the second term, which is this. Maybe I should put brackets around this one too. Forget about the equals 0 part, we don't need that now. So you multiply that times k times e to the t to the 0.5 power minus 0.12. Plus what?
The derivative of the second.
Yeah, the derivative of the second term with respect to t, which Brianna is, we'll put our plus here.
0.5 t to the negative 0.5.
Yeah, it would be,
0.1.
yes, it would be 0.5 t to the negative 0.5 minus 0.1. Oops, what am I doing? It's minus 1 here. Minus 0.1 is down here. That's just the derivative of this exponent with respect to t. That gets multiplied times what? This whole term, k e t to the 0.5 minus 1.2. All of that is just the derivative of the second term times the first. Times, don't forget about this first term. Just to repeat. Take the derivative of this term times this term. That's what we did here. Plus the derivative of this term, which is this, all of this, times the first term. And what can you observe about that? We're evaluating the second derivative at the critical value of t. Now, what was the first order condition? What had to be true about this term right here?
Equals
It had to be 0. So this term right here is a 0. By the way, so is this one. One of them would have been enough. Both of those are 0, so all of that, all this stuff right here just drops down. So this reduces to just this. Second derivative reduces to minus 0.25 t to the minus 1.5 times this. And that negative sign there guarantees negative. So the second derivative is negative at the critical value of t. So we have a maximum at t equals 25. So if you want to maximize the value of wine, you age it for 25 years. And then at this point, you would want to go back and say, okay, what is the present value? And you just plug into the present value formula. T equals 25. And this would be your max. Okay, I'll let you do that. Just plug in T equals 25 into that formula for the present value. One important notice, and Gene sent you a memo a few days ago saying tomorrow, Thursday, right? Sometimes I lose track of what it is. Tomorrow's Thursday. You have graduate orientation at, I don't know, 9:30 or 10 o'clock, something like that. So tomorrow we will meet at 1, starting at 1 o'clock, so you can attend your graduate orientation. I wouldn't want you to miss that. So tomorrow we'll meet at 1 o'clock. And what we're going to talk about tomorrow? We're going to talk about optimization problems when you have two or more choice variables in your objective function. That would be the subject matter of chapter 11. So we finished chapter 10 today, that's good. We'll have we'll start off tomorrow with a quiz as usual, and then we'll talk about chapter 11. So we're moving right along. See you tomorrow. Jean, did you want to say
I
anything?
was just going to say that, don't forget